Hello, good morning, or good afternoon, or good evening. You guys do your best work at night, don't you? I do my best work in the morning, but I'm having a strong coffee right here. Let's see if we can balance some chemical equations. If you need more practice, maybe you don't. Never hurts, right? So here's the chemical equation. Nitrogen gas, hydrogen gas, NH3, ammonia. But you know what? There's two hydrogens over here, and there's three hydrogens over here. How do you make... oh, no, wait. Let me see it this way. Let me start over here. And so you can tell I call this the guess and check method. I'm just checking around, guessing, looking at elements on the left side of the arrow, looking at elements on the right side of the arrow. These are the reactants. These are the products. You should know those terms, right? Nitrogen, N2, but there's only one nitrogen over here. So what do? I do not stick a little 2 right here. That would be a huge mistake and a grievous sin in chemistry. That's changing the compound. But no, I stick a big fat coefficient integer, a whole number, right here. So I get 2 n's, and to match the 2 n's over there. It doesn't look exactly the same, right? But I'm thinking about 2 molecules over here. In that case, the 2 also stands for 2 of these. That's 3 h's. 3 h's times 2 is 6 h's, so guess what number I stick right in front of the h? And that's my balanced equation. Interesting. Yeah, next I put sulfur burned in oxygen. Might give sulfur trioxide, but of course this side has 2 O's and this side has 3 O's. I can't change this 2 to a 3 or this 3 to a 2. That's a big mistake, but I can put something here and something here. And when I'm trying to make a 2 and a 3 balance out, yeah, I just take 3 here and 2 here. That gives 3 times 2 is 6 and 2 times 3 is 6. But the sulfurs then get thrown off because I put a 2 here, 2 sulfurs, so I better get 2 sulfurs over here. Voila, balanced. I just thought of something. I should draw some ball and stick pictures to help us think about what in the world's happening on some of these. Phosphorus, oxygen, tetraphosphorus decaoxide. So this side has 10 oxygens, this side has 2 oxygens, this side has 4 phosphorus, this side only has 1 phosphorus, so perhaps I might want to stick a 4 in front of the phosphorus to balance the 4. But then easily I can balance the oxygen as well, without changing anything else. And lo and behold, there's my balanced equation. 4 phosphorus atoms and 5 oxygen molecules react to give 1 molecule of phosphorus decaoxide. Try that again. Here's the decomposition of potassium chlorate into potassium chloride and oxygen gas. The only problem is the O3 and the O2 don't match up. I must have the same number of oxygens on both sides of the arrow. Reactant products. So you know what to do, don't you? Do you know what to do? Yeah, you do. You stick a 2 in front of here and a 3 in front of here. That balances my oxygens with 3 times 2 and 2 times 3 oxygens. But of course that generates 2 potassiums, 2 chlorines. So what do I stick here? You know the answer. Well, maybe not. Maybe we're just learning. Maybe we're practicing. That's why we're here. To practice, to learn. Here's a tricky one. I think we've seen this one before somewhere. This was a lecture clicker, I believe. 1 sodium, 2 hydrogens, 2 hydrogens. Whoops, there's 1 more hydrogen there. So you know what? This is an even number of hydrogens here. This is an even number, but there's an odd number here. This odd number of hydrogens will never balance this with this even number of hydrogens unless I stick an even number in front of here. And the simplest even number I can think of is 2. Of course, that throws off my sodiums, but I'll worry about that in a minute. 2 hydrogens here now and 2 more hydrogens here adds up to 4, so I can get 4 hydrogens here simply enough by sticking a 2 in front of my water. That gives me 4 H's left and 1, 2, 3, 4. So 2 H's and 2 H's is 4 H's. That gives me 2 oxygens on the right and also 2 oxygens on the left. So the only thing to do is to fix this up. 2 sodiums on the right, 2 sodiums on the left. Now that's balanced. And this very similar pattern will go with lithium in water, potassium in water, cesium in water. Alright. Here's a fun one. Zinc into silver nitrate. Sometimes it's easier to think about these polyatomic ions like nitrate not breaking up, so I'll leave that nitrate together and think about one nitrate NO3 over here and two nitrates NO3 over here. So if I have two nitrates over here, I better get two nitrates over here. So I stick a big fat 2 right in front of that silver nitrate. That gives me two NO3s, just like these two NO3s, but of course that gives me two silvers on the left, so I want to get two silvers on the right, and there's one zinc, and there's one zinc, and voila, fini, done. Let's try another one. One aluminum plus hydrochloric acid, and aluminum would be eaten by a strong and concentrated hydrochloric acid to make hydrogen gas and aluminum chloride aqueous. Say more about that in a bit maybe. But of course that's not balanced. I got 3 chlorines here, 3 chlorines here. I'm sorry, 1 chlorine here, 3 chlorines here. Another problem is I have 2 hydrogens here and 1 hydrogen here. Well, I might think just to stick a 3 right here. And I could. 3 chlorines, 3 chlorines, 3 chlorines, 3 chlorines. But if I stuck a 3 here, that would give me 3 hydrogens, which is an odd number, which will never balance this even number unless I make that number in front of this hydrogen an even number. So I did. I made it a 6 and make that a 2. 2 times 3 is 6 chlorines. 2 times 3 is 6 chlorines. 6 times 1, 6 chlorines. And 6 hydrogens, and 1, 2, oops, that's not balanced. Let me get 6 hydrogens on the right, putting a 3 here. 3 times 2 is 6 hydrogens to match those 6 hydrogens. And the only thing left to do is take 2 aluminums and 2 aluminums. Done. Balanced. Interesting. Strontium chloride and ammonium carbonate. Let's see, let me think about this. Ammonium is not busting apart, so this polyatomic ion stays together, NH4 plus, and I have one NH4 plus over here, but I had 2 over here. So let me just stick a big fat 2 in front of here. This gives me 2 NH4s, ammoniums, 2 ammoniums, 1 carbonate, 1 strontium. Ta-da, done. Right? Yeah, done. This is a fun one, very common. Hydrogen gas, oxygen gas, 2 H's here, 2 H's here, 2 oxygens here, 1 oxygen here. So I better stick a 2 in front of here, get 2 oxygens, but that screws up my hydrogens. 2 times 2 is 4. So I just come over here to get 4. So this is my balanced equation right there. Another polyatomic one, this nitrate. Whoa, that's similar to one we've seen. Oh well, let's do it anyway since I have it written down. 1 nitrate here, 2 nitrates here, so I might want to come over here and get 2 nitrates, the NO3 groups. That gives me 2 silvers left. Let me just go ahead and get 2 silvers right. And I have 1 zinc left and 1 zinc right. Did I say 2 chlorines? 2 chlorines. 2 chlorines right and 2 chlorines left. Let me show you a more difficult process. That would be looking at some verbal description in words of a chemical reaction and trying to translate it into symbols and then balancing. Oh my goodness. Solid ammonium dichromate decomposes to give nitrogen gas, water vapor, and solid chromium 3 oxide. This is a fun demonstration. I'll show it to you sometime in class. So I have ammonium and dichromate. If you don't remember the names of the polyatomic ions, you look them up. This is a +1 charge. This is a -2 charge. So I took 2 +1s, 2 +1s to match the 2 minus of the dichromate. This little triangle means heat when it's written over the arrow in a chemical equation. Nitrogen gas, N2. Did you know nitrogen gas was N2? Like oxygen gas is O2 and hydrogen gas is H2. Water vapor, water gas, and solid chromium 3 oxide. Chromium 3 oxide. Interesting. Looks difficult to balance, but it's not that bad. Check it out. 4 hydrogens here, but there's 2 of those. So 2 times 4 is 8. So how do I get 8 hydrogens over here? Voila. And believe it or not, that should take care of all my oxygens too. This side has 4 oxygens here, 3 oxygens here for an odd, literally and figuratively, 7 oxygens. And this side had 7 oxygens as well. 2 chromiums, 2 chromiums, 2 nitrogens, 2 nitrogens. That was so much fun. Let's try another one of those. Dilute barium hydroxide reacts with dilute. Dilute means kind of watered down. Not hugely watered down, but not too concentrated to make it dangerous and scary. To create water and barium sulfate solution. So here's barium hydroxide. Perhaps I should have said dilute barium hydroxide solution, but I'm assuming that aqueous in water. And here's my sulfuric acid in water, and I create barium sulfate and more water. So the water is here, and the barium sulfate solution is right there. But that's not quite balanced. Let's see, I had, it looks hard, but it's not that bad if you look at it like this. Here I have two hydroxides. Here I have two H's, hydrogens on the acid. So this is a base with the OH, and this is the acid with the hydrogen in the front. So these two H's go over and meet these two OH's and just make two waters. And there you go. That one's balanced. Interesting. Do we have time for another one? Yeah, maybe. Solid tetraphosphorus decaoxide. You know I'm going to skip that. You guys can look at it on the PDF if you want to. Chances are that I would wake up on the wrong side of the bed if I asked a test question like this, but it's possible. Here's a good one. Liquid methanol is burned in air, creating carbon dioxide and water. Whenever you burn something, you almost always get carbon dioxide and water. This one's fun because I have, let's see, I have 4 hydrogens left and only 2 hydrogens right. So you might guess to put a 2 here. 2 times 2 is 4 hydrogens to match those 4 hydrogens over there. Let's see, then I might guess that if I had, let's see, oh yeah, check this out. Here's 2 oxygens on the right and 2 more oxygens on the right for a total of 4 oxygens on the right. On the left I have 2 oxygens here and 1 more here. So I might guess to put a 2 in front of the here, in front of the alcohol to get 2 oxygens and 2 more oxygens for a total of 4 to match those 1, 2, 3, 4 oxygens. But that kind of puts a 2 in front of the carbon, so I'd have to put a 2 here, and that throws off my oxygens. So I got a wee bit of a problem. And also, yeah, what was I going to say? I forgot my train of thought. Oh, great, there's the telephone. Sorry, hang on a second. All right, I think I got this nailed down now. Let me try this. Yeah, so I had 2 oxygens and 2 oxygens, total of 4. But when I do that over here to get 4 oxygens, and I create more carbons, and so I need to get, I'd have to get more carbons over here, but that would throw that off again. Oh, more importantly, to throw off my hydrogens. I got 4 times 2 is 8, and I don't have 8 over here. So I thought maybe, let me bump it up a little bit. Bump it up to the next largest even number, trying to make everything balance out. Let's see, 4 times 2 is 8, and then 4 hydrogens times 2 is 8. 2 carbons here, so all I have to do is put a 2 here. Yeah? And I'm almost done. Now I can put anything I want in front here without throwing off any of the other elements. I can balance my oxygen. Let's see, 2 times 2 is 4, and 4 more for a total of 8 oxygens. This side has 2 oxygens here, so I need 6 more. So how do I get 6 out of this? Yeah, this better be right. Boy, if I screwed that up, I'll be embarrassed. I think that's right. Check it out. You will enjoy catching me if I made a mistake. Here, I'm just going to scroll through this. You can take a peek at this one. It's good to know some of the common names like ammonia, nitrogen monoxide gas. But let me just cut to the chase here on why are we balancing these equations? Because we really want to know the stoichiometric ratios that these lead to. In other words, this is from earlier. 2 of these compared to 6 of these, or 2 of these compared to 2 of these, or 2 of these compared to 3 of these, or 6 of these compared to 2 of these, or 6 of these compared to 3 of these, or 2 of these compared to 3 of these. And those are the 6 molar ratios that you can think about for this one balanced equation. Or, if you don't like that, or even if you do like it, we could say any other number, any other relative amount of this and this and this all work out. For example, a hard one would be 1.72. Well, if there's a 2 there and there's a 2 there, these two are the same. Tut, tut, tut. But if there's a 6 here, this 6 is 3 times more than the 2, so I need 3 times more moles of HCl than aluminum. And this one's a little bit tricky. 3 here. About 3 is half of 6, so this amount is twice this amount. Thanks, guys. I'll see you in class. That's enough for one setting.